Hi everyone, and welcome to Jam Academy. Now, this example, the objective of me doing this example is to help you know how to apply the work kinetic energy theorem. The work kinetic energy theorem is one of the most important theorems in classical mechanics. It falls in the same category as the impulse momentum theorem. And when you look at it critically, both are all connected to Newton's second law of motion. The work kinetic energy theorem essentially states that the net work done on a system is equal to the change in the kinetic energy of the system, which means that if the net work done is positive, there will be an increase in the kinetic energy of the system because energy is transferred into the system, and consequently, the speed of the system will increase. On the other hand, if negative work is done on a system, now negative work is when the system does work on the surrounding. Now, when the net work done is negative, then the kinetic energy of the system decreases. Obviously, the system uses up some of its energy to do work, because work done essentially is energy transfer. The consequence is that the speed of the system will decrease. A typical example, as we will see, is a car doing work against friction as during the stoppage period. And that is exactly what we are going to do here. Now, specifically, the problem says that an automobile of mass m is traveling on a level road with a constant speed v. At an instance when the brakes are locked, the tires of the car slides across a section of the road whose coefficient of friction is mu. We are required to use the work kinetic energy theorem to calculate the minimum stopping distance of the automobile in terms of given quantities. Now, remember, by definition, the work kinetic energy theorem states that the total work done on a system is essentially equal to the change in the kinetic energy of the system. Now, so how do we calculate the net work done, and how do we calculate the change in kinetic energy? Remember, when you are applying the work kinetic energy theorem, the very first thing that you need to do is choose the initial point and the final point. Now I'm going to choose my initial point. This is my initial point A, and this is my final point B. Now at B, the car comes to rest, which means that the kinetic energy at B is equal to 0. At A, the kinetic energy of the car at A is going to be equal to 1/2 mv squared, where v is the speed of the car at A. Now, the distance between AB, I'm going to just call that distance x. We are required to calculate x, the minimum stopping distance. The minimum stopping distance. Now, the next thing that we need to do is to calculate the net work done on the car. To calculate the net work done on the car, we need to know the forces acting on the car. The best way for us to keep track of the forces acting on the car is to draw a free body diagram. And what is a free body diagram? A free body diagram is simply a diagram that shows us the forces acting on the car, not the forces exerted by the car. And by the way, we are interested on the work done on the system. So if we do that, we have the weight of the car acting vertically downwards. I'm just going to call this mg, which is traditionally that way. The normal force acting perpendicular to the surface, I'm just going to call that n. Then we have the friction force acting in the opposite direction of motion. This is kinetic friction. Remember, the car is sliding. If the car was rolling, then the friction between the tires of the car and the road will be static. and will be pointing in the direction of motion. But because the car is sliding across the road, the friction between the tires of the car and the road is kinetic and will be opposing the sliding. So that being said, you can automatically see that the sum of forces in the y direction is 0. That means, that implies that N is equal to mg. Similarly, we know that by definition, the kinetic friction between the tires of the car and the road is going to be equal to mu, the coefficient of kinetic friction. I'm going to use a subscript mu k and multiply by N. This is going to be equal to mu k mg because N is just mg. So the total work done on the car will be equal to Fk multiplied by x cosine of theta. If you look at this carefully, the car is displaced forward, but the friction is acting backwards. So the angle between the displacement and the force is 180 degrees, and the cosine of 180 degrees is -1. So this is just going to be equal to negative mu k mg multiplied by x. This gives us the total work done on the car. Now, by the work kinetic energy theorem, the total work done on the car is simply going to be equal to the final kinetic energy minus the initial kinetic energy. This is 0 minus 1/2 mv squared. Hence, we can conclude that negative mu k mgx is equal to negative 1/2 mv squared. The beauty of this equation is the fact that m, we can divide both sides by m, which means that the m's will go away. And we are looking for x. We are looking for x. And if that is the case, we can see that x will be equal to v squared divided by 2 mu k multiplied by g. Right here, this gives us the minimum stopping distance traveled by the car after the brakes are locked. Now the next part of the question says that by what factor would the minimum stopping distance change if the coefficient of kinetic friction were doubled? By what factor will the minimum stopping distance change if the coefficient of kinetic friction were doubled? So remember, I'm going to use a different color. Mu k prime is equal to 2 mu k. So this would mean that x prime will be equal to v squared. The speed stays the same. 2 bracket 2 mu k g. This is just 1/2 v squared divided by 2 mu k g. In other words, this is just going to be equal to x divided by 2. If the coefficient of kinetic friction doubles, the stopping distance reduces by half. That makes sense. If the friction between the tires of the car and the road doubles, obviously we expect the stopping distance to decrease. Now the next question is, what will happen to the minimum stopping distance if the initial speed were doubled? Remember, if the initial speed is doubled, while the coefficient of kinetic friction stays the same, we're going to have a very comfortable scenario here this will be x prime will be equal to 2v all squared divided by 2 mu kg. This is going to be 4 bracket v squared over 2 mu kg. In other words, this will be equal to 4x. It will be equal to 4x. So we have just proven that if the initial speed of the car doubles, the stopping distance increases by 4. The stopping distance increases by 4. So you need to watch your speed. The recommendation based on this question is that you need to reduce your speed whenever you're about to stop, because that will decrease your stopping distance. Part 3 says that if the coefficient of kinetic friction and the initial speed were both doubled, well, it will stay the same. You can prove that for yourself. And when you do that, you will send me a solution as an extra credit in class. The stopping distance will remain the same in this particular case. Now, this is an example of classic problem that you will meet maybe in a test, a quiz, or in an exam, but it illustrates comfortably the application of the work kinetic energy theorem. It is my pleasure to bring you these lessons, and if you need help, please do not hesitate to contact me by participating in the discussion forum below this video. Thank you so much, and remain blessed. Bye-bye.